Good. Oh, I missed the thumbs up. Okay, great. Hi, everybody. Sorry for that kind of awkward transition. My name is LeClerc. I am a mathematical statistician working in this really lengthily named suborgan of the United States Census Bureau. You can just think of it as it's sort of the area at Census that is responsible for disclosure avoidance concerns, and that has sort of adopted differentially private methods for a lot of our current initiatives going forward. So this is a quick description of just a number of the folks I work with. This is not an exhaustive list. I kind of selected the subset of people who spend most of their time working with me and other folks on mathematical theory, privacy theory, implementation of code, and then also sort of manipulating the data sources that we work with. And so I think maybe not all of you, but some of you may be familiar with John Abad. He's the project lead. He kind of sets sort of high-level visionary decisions for the project. Someone else that I probably should call out is Dan Kiefer, down here in the academic partners section. He's the scientific lead and has made some sort of high-level algorithmic decisions for the way in which we're processing our data and trying to actually implement the final DP mechanism that we're developing. So what I intend to talk about today is first, so it's split up into sort of these three major areas. First, what is the 2020 Disclosure Avoidance System? So DAS is kind of the acronym that we throw around when we're talking about the system we're building. And that's actually not the main point of the talk, although it will take us a while to get through. The point of that is to provide sort of context and motivation for the practical obstacles that I'll talk about at the latter half of the talk. And then we'll jump into two classes of practical obstacles that I want to discuss that I think to some extent have been understudied, and maybe we can draw a little bit more attention to them. So first is challenges that occur in estimating error, and second is my really terribly named topic, challenges with practical implementation. And so I really struggled to come up with a better name than practical implementation issues for that second category, but hopefully when we get to that section, it'll be kind of clear what I mean by that. And then in the end, I'm going to just stop and say, oh, also there's a lot of other stuff that I wanted to talk about but couldn't talk about because an hour wasn't enough time. And so I'll probably linger on that slide at the end and just let folks stare at it. So what are we doing at Census, and what have we been doing for, say, the past 2 years on this project? So our goal is to develop a formally private census, whereby formally private, I don't mean differentially private specifically, although differentially private algorithms will perform like sort of the primary subroutine that it confers privacy for the algorithm. But formally private in the sense that there should be some rigorous mathematical proof for broad classes of attackers that has a clear privacy guarantee in the usual sense that you sort of encounter in the DP literature. We'll talk in a sec a little bit why I can't just make the claim that it's fully DP. So before we do that, and we'll actually get into it while I'm working down this list, there are sort of a number of structural decisions we've either made or had imposed upon us or were sort of requested of us as we were designing the DAS. This first little list here is sort of the list of inputs that we're expecting the DAS to take in. So the first of these is the CEF, the census edited file. You can just think of this as the sensitive input data. So this is the 300 million odd records for persons that we're collecting. And there's also 100 million or so odd records for households that are collected as part of that same input source. And so this is the sensitive input data that we were interested in protecting, and also in which we are interested in preserving reasonable amounts of utility and accuracy for end users on. There's a second class of inputs here that I refer to as invariants. This is sort of a term that we have developed internally for discussing this particular class of queries. And this is the reason I can't claim that the system is end-to-end differentially private. So these queries, which I'm not going to talk too much about today unless people have questions about them or want to talk about them afterwards. These are queries that just, we are not allowed to infuse any noise into them. And so when we generate our eventual microdata, which is what we're going to produce internally, that microdata has to agree exactly with the original CEF on the values of the invariants. And yet we wish to model sort of our responsibility for releasing the information associated with these invariants. And because of that, we have to modify some of the standard semantic guarantees and some of sort of the high-level claims we make about the privacy guarantees of the end-to-end system.
As you go along, can you point out which invariants are legally mandated and which are there for other reasons, like because it was too big of a headache to argue about or something like that? So
we're not going to get too much into the details of the invariants today. I can say, by way of example, that there will most likely be an invariant for the national population, as well as invariants for the state level populations. Whether those are legally mandated or not is a sort of fraught question that I am not the right person to sort of decisively answer, but there are clearly legal concerns associated with those quantities. There are also other classes of invariants that maybe get into the second category you mentioned, which are not in any sense legally mandated, but which are sort of kind of unavoidable given the way processes currently work. So the category I usually go to for this example is we have, and we'll get to this in a second, we have a bunch of tabulations that are published about what are called group quarters facilities. So these are tabulations about people that live inside college dormitories, military bases, that sort of kind of large scale group structure. Because of the way those queries are actually collected in practice, and I don't think I'm really the right person to get too much into detail about how that works, but because of the way they're collected in practice, working with sort of members of the communities that are relevant, that information is kind of already publicly released or in the public domain in some sense, and so there's not really a way for us, certainly not at this point in the processing, to claw that information back and sort of say, no, we're going to hold that behind the privacy barrier. That isn't something we can do at this point. In addition, there are also, there's a larger class of sort of potential invariants that are kind of under discussion. One example of this is that there has been discussion about whether or not the number of persons who are of voting age or non-voting age within individual geographic units should be held invariant. There have been similar discussions about whether the total number of households in a geographic unit should be held invariant, or whether the total number of households that are occupied should be held invariant. And so there are a lot of decisions kind of swirling around exactly what this set of invariants will finally look like. And actually the uncertainty about what that set's finally going to look like has driven a lot of our design decisions and controlled a lot of the work that we've done in trying to make sure that we can anticipate whatever those are eventually going to, what form they're going to take. So hopefully that just addresses most of what you're asking about, or some of it anyway.
Thank you.
So there is a third major input here, which I will refer to as the workload, and denote by W. I'm borrowing this language from the matrix mechanism paper, if you all are familiar with that. You can just think of it as the set of queries in which we are attempting to minimize error. So these are the queries in which we are going to sort of, with our noisy differentially private measurements, attempt to get decent fit, but it won't be exact as in the case with the invariants. Okay, so given these inputs...
One more invariant question?
Yeah, go ahead.
The other place where you would use invariance is to be sure your software isn't dropping one, at a roll-up at various stages, and that's a common checking procedure. Do you have things like that, or is there a wall behind you can keep that stuff?
I'm not sure I entirely follow the question. Could you elaborate a little bit?
Well, you introduce 999 new records, and the count goes up by 1,000. That shows that's a common sort of transient error in building software that is absorbing stuff all the time. So does that survive, or do you lose the ability to look for those little glitches?
So this is actually one of the practical implementation difficulties that I kind of want to discuss a little bit later in the presentation, because it is exactly the kind of thing where we are interested in being able to hunt for bugs that may have generated errors that are sort of abnormally large and sort of are of unreasonable size, and that suggests that there is an error in the implementation. That being said, we can't readily do that by just jumping into the true data and jumping into the final produced microdata that's privatized and comparing them directly to one another, because if we do that and then we start making changes on the basis of that process, we've sort of introduced a feedback loop, and the final randomness that governs the actual outputs is no longer necessarily governed by the DP definition, but ends up being governed by sort of our subjective interventions to try and control those kinds of errors. But we'll talk a little bit about that. I don't know that I will have a satisfying answer for that question. We'll talk a little bit more about it. Okay, so given these inputs, there are some expectations that we're trying to meet as far as the form of the outputs that we're producing and sort of the properties that they'll have. The most important of these, I think, is that we are expected to generate microdata. There are a few reasons for this. One of the most important ones is that it fits really nicely into internal processing pipelines, so folks are already sort of accustomed to dealing with microdata. A second, so sort of maybe less convenience-based reason, is that it also allows us to ensure that there's consistency between the queries we're publishing in a really easy way, and that they don't sort of look strange in various cases. So you want to make sure that there aren't negative queries floating around in the tabulations that we publish. That tends to be a difficult thing to explain when you're talking to, especially a non-technical audience, about why that estimate was produced, or when you're trying to interpret it in some sort of more concrete sense. I also have two other requirements listed at the very end here. This is really just a restatement of sort of what invariants are intended to represent, and also a statement that when you look at the way the DAS is organized, At least for the first few data products, this may not be its final form, but for the first few data products, the DAS is going to look like generate a microdata detail file. This MDF is the microdata we're generating, which will pop out of an algorithm known as the DAS, which takes as inputs the workload because it needs to know what it's trying to get low error on, but will also take as inputs the true values of the invariants evaluated on the Ceph, so evaluated on the underlying true data, and which will also take out so measurements evaluated on the Ceph as well, so DP noisy measurements, estimates of those queries that we're interested in trying to get low error on. Are there any further questions about this slide? Take that as a no. Okay. So jumping into the workload a bit more, I think in attempting to motivate and explain what we're working on and sort of the problems that have popped up, one of the easiest ways to grapple with the project and sort of come to understand how it operates is to first start with what the problem looks like and what the structure of our workload is, because that's really where most of the structure of the problem comes from. So the workloads, or rather the queries in the workload are organized along a number of different dimensions. So first they are organized in sort of a geographic dimension. They live inside geographic units, which live inside geographic levels, and those have sort of their own structure that we'll talk about in a slide or two. In addition, as I've sort of already kind of alluded to in answering one of the early questions, there are two kinds of records, at least two kinds of records that we're dealing with. There are person level records that we have to address queries on, as well as queries that are sort of about units. So about the people who live in a household that have a householder who is of a particular race. That is a common example of a query in the second class. And in addition, there are, I think not so much for group quarters facilities, but at least for households, there are literal counts of the number of households satisfying certain properties. And so we have a number of sort of group queries and person level queries. Usually we reason about sensitivity by thinking about neighboring databases in terms of alterations to individual persons, not to individual households. So this is one, these are the first two ways in which the workload is organized. Moving on a little bit more, we then, and this is actually how I sort of day to day think about the actual algorithms we're building and sort of how much progress we have or haven't made and what major milestones we still have to meet. The releases that we intend on producing are then typically organized into 4 major data products and roughly 10 additional smaller data products. The 4 small data or the 4 major data products are PL94, SF1, SF2, and AINSF. PL94 stands for Public Law 94-171. This is the data product that is associated with and used for political redistricting. And so usually when you think about constitutional mandates or sort of the strongest legislative requirements, they tend to pertain immediately to this data product. This is the smallest of the 4 major data products, but it also tends to have the lowest geographic resolution of them. It includes queries like how many people are there that are of voting age in a particular geographic unit, how many people are there that are of non-voting age in a particular geographic unit, how many people are there in a geographic unit that reported having being of 3 races, of 4 races, of 5 races within the 6 major race categories that are reported in the census, and there are a few other queries in there as well. The next major data product, stepping on up from that, is Summary File 1. Summary File 1 is very similar to PL94, but bigger. So Summary File 1 takes the kind of demographic information that appears in PL94, and it says, well, for example, you only had voting age, non-voting age in PL94. As it turns out, there's a wide range of user communities that are interested in having a lot more detail in the age distribution than that. And so Summary File 1 at the census tract level, which is a geographic unit we'll talk about in a second, but just think of it as not the lowest level, a little bit above the lowest level. At that level, Summary File 1 in 2010 contained tables that were at single year resolution of age, and so it would count like the number of persons who were of age 37 and male in a particular geographic unit. And it sort of generally, it just sort of takes the dimensions that were in PL94, adds a number of dimensions to them, and increases the resolution within each dimension, while still going down to the lowest geographic level in some cases, higher geographic levels in a few other cases, and it's spread across the census block, census tract, and county levels. And again, we'll talk about the geographic hierarchy in a second. Maybe I should have put that slide before this one. But so let's jump on to Summary File 2. So Summary File 2 and actually AINSF, let's treat them together. So Summary File 2 is sort of a detailed race version of Summary File 1, and AINSF is sort of a detailed tribe version of Summary File 1. Both of these data products take a subset of tables from SF1, and they say, okay, you had whatever the variables were in the table originally, and you sort of formed the full cross of them and counted all of those individuals that fell into each of those buckets. We're now going to take each of those tables, and for SF2, we're going going to cross them by the one of 500 or so individual detailed races. And for AINSF, we're going to do the same thing, but cross them now by one of about 1,500 individual detailed tribes. The geographic resolution is coarser for these two products than it is for the first two products. But I think you can already see, both from the level of detail that's sort of popping up in those race and tribe dimensions, as well as, we'll talk in a second about the number of geographic units there are, how we're getting to these large numbers that I have sitting next to each of the data products.
Where are the 500 races coming from?
So I could show you the full list, but I'm not an expert on how the list is actually cultivated and sort of originally created. That's maybe a good question for us to sort of circle back around afterwards, when I can actually go to like the relevant resources.
Because it counts combinations though, right? If you say you're multiple, so is it just... So there is a little bit of, the short answer is yes, but in the SF2 and AINSF products, the numbers that I just quoted, the 500 and the 1,500, those are not because it's taking all possible subsets of a set. Those are because there are roughly, I think, 250-ish individual detail races, and then you get roughly twice that because it asks about them individually, and then it also asks about them and whether or not you also reported being something else. So there is the detailed race alone and the detailed race in combination with some other race. This is excluding the major OMB race categories, which is I think what you may be thinking of. The major OMB race categories, there are only 6 of the binary flags for them. And those will contribute to both PL94 and SF1, not just 6 sort of levels in a dimension, but 63 levels in a dimension. And that is because in these two products, those major race categories, you do form sort of all possible subsets of them. And look at each of the subsets.
So just, sorry.
That's okay.
I don't remember looking at the list of questions for the decennial census. I don't remember anything beyond the 6 categories. So is this from the ACS?
It is not from the ACS, no. It's a write-in, there are write-in blanks on the decennial census form, and folks can use the write-in blanks to indicate, well, so I don't consider myself just Caucasian, I also consider myself Italian, or I'm Czech, or so some other sort of detailed race category that can be listed. And I can show you the list of them for 2010, maybe after the talk. So the key point here is that there's a lot of data products with a lot of tabulations in them that have been published historically. These counts here are actually kind of a mix of what the historical estimates look like and sort of what I sort of currently expect the future-looking number of tabulations to look like. For PL94 and SF1, these two counts, those are reasonably close to sort of what I expect to be confronting for 2020. For these other 3 categories, it's still a little bit more up in the air. This one mostly just because I realized this morning my code wasn't doing quite what I thought it was doing. These two because these products are so large that traditional methods will not work with them, and we also, I think at Census, are probably going to end up having a fairly hard conversation about whether it's actually possible to deal with simply the sheer number and complexity of those tabulations.
So I guess PL94 is needed for specific legal reason of redistricting. Are there specific legally required use cases for the other 3, or we give them because we like to share data?
It's really hard to give a terse answer to that. So the reality is that there is not sort of a single centralized database that collects all of the legal justifications for and/or uses of each of the individual tabulations that are published in the census. So that's kind of a murky answer, but it is also the case that these other products, SF1, SF2, and AINSF, are many of their tabulations, I would be hard-pressed to sort of extemporaneously identify all of them, but many of their tabulations are used in the execution of various laws, whether those laws at the state or federal level or county level sometimes call for using that product specifically, or they just say sort of use the best available thing and they default to the decennial census is sort of a hard thing to get good statistical information on. But so the answer is yes and no.
So is there an institutional memory of which wars were fought by the definitions in categories 2, 3, and 4?
I think there is an institutional memory of recent-ish, maybe over the past decade or 2, conversations about individual tabulations, but I would not go as far as calling it an institutional memory for the war fought over every individual tabulation. I don't know that there is sort of like a log file that is just petabytes and petabytes long that describes all of the individual conversations that surrounded each of the individual tabulations. The recent effort we made to try and gather some of this information, so there's also maybe something else to be said about this too, before I jump on. Part of our effort to learn a bit more about how this is being used, because a lot of this sort of, once it leaves Census's borders, it ends up being repackaged by other organizations. So like IPMS is a very large repackager of data that's published by the Census. once that information gets out into the world, it's used in a lot of ways that we sort of have no immediate ability to track. And so even stepping away from like specifically statutory uses of the data, it's also really important to understand, well, I mean, how are researchers using the data? How are medical organizations using the data? How are cities using the data to make planning decisions? And so we had a federal registry notice that went out to try and gather some of that information, and we got some useful feedback, but I think there's still definitely a need for us to engage more thoroughly with sort of the external expert user community about a lot of the use cases. Or maybe a partial answer to your question. So I think this is probably obvious to everybody, but we have about 300 million person records, about 100 million household records. Given the sheer number of tabulations that you can see sort of further up on the slide, it can be expected that most of those tabulations are going to have an answer of 0. There's really no way around that, short of just making them all exactly the same tabulation, which I can assure you folks did not do. This is the geographic lattice I promised we would talk a little bit more about. I don't want to spend too much time on it. This is a really helpful visualization that you can get by going to the Census geography website. So I literally just went there and sort of screen captured it. It shows you all of the different geographic levels that are used sort of in common parlance and application at Census. And for us, of particular importance will be this sort of central geopath, as I refer to it, which drops from nation to states to counties to tracts to groups and to blocks. And there's also kind of well, this block group is already there. So we're going to, within the DAS, walk down that hierarchy in the generation of our microdata product. And that will sort of dominate the organization of the algorithm. These other areas are also quite important, and sort of there are some questions for me at least about whether we can find a way to explicitly spend what I will refer to throughout the talk as privacy loss budget, so sort of expenditure of DP epsilon on targeting accuracy in some of these other geographic areas. But it's maybe important to call out that a key property of this lattice is essentially everything can be built from census blocks. So you can think of census blocks as sort of the atomic unit from which everything else is constructed. There are also a few other features of this chart that may be worth observing. So certain of these areas, urban areas, for example, don't partition the nation. So not every area in the nation is urban. This is sort of a bunch of non-exhaustive subsets of the nation, and that you can think of as aggregations of blocks. And so throughout the talk, I'll refer to these as geo units, things like Texas that live inside geo levels, things like states. One other thing to mention about this sort of picture is this is where a lot of the scale in the workload we looked at comes from. So in particular, at the census block level, there are something like 10 million census blocks. That's a really crude approximation, and John might actually poke me a bit for using so crude an approximation. But you can find that online. It's a good order of magnitude estimate of how many census blocks there are. And that's how we get into the billions with a lot of those figures. Okay, so I've talked a lot about things that make our problem hard and sort of like the complex structure of our problem. I should also mention that we do have a few things that make our problem somewhat easier, which are rather nice, and some that are less nice. But the thing that was nice that I'm thinking of is that most of our queries are low sensitivity counting queries in the usual differentially private sense, the usual sense that term is used in the literature. We also have some sort of high sensitivity queries on person HHGQ joins, which are sort of noisy measurements we would like to take in order to figure out, well, if we're going to be asked to take people and put them into households and provide the ability to join the two microdata files, if we're going to be asked to do that, then this is a class of queries we would have to face down. I'm probably not the right person to speak to methods for doing that. Some of our academic partners have some ideas about it, but it's still sort of a topic of conversation. And we've also pitched sort of some heuristics for trying to alter the workload in a way that would make these things sort of analogous to what they are, but lower in sensitivity. In addition, there are also nonlinear queries, medians and means, which I don't think we have any present plans to try and directly target them with privacy loss budget, but the medians and means, for the most part, they can be expressed as nonlinear transformations of the counting queries. So I think we have at least ways to support expressing queries on them and tabulations over them from the final microdata, but I don't think we're going to be spending privacy loss budget directly on them. And then this table at the end is just a simple example that you can get if you Google SF1 PDF 2010 technical documentation. There is a 600-page technical documentation document. You can drop down into chapter 6, subsection 3. It's the data dictionary section. That section has a whole lot of tables that look like this. And so you can just see this table says in SF1, tell me how many people there were who reported being of 2 or more of the 6 major OMB race categories. Tell me how many people there were who reported being of that type in total. Tell me how many of those folks there were who were male. Tell me how many of those folks there were who were male and under 5 years, and also in each of these individual age buckets. So this is sort of a concrete example of some of the tabulations that we're dealing with. Okay, so given the complex structure that we've just kind of looked at, how do we actually go about trying to contend with that in practice? Well, the way the DAS organizes its work is it actually does it very similarly to the way that we've laid out this conversation so far. So it works currently over sort of pairs of major data products and record types. And for each major data product, which is something like PL94, SF1, SF2, or AINSF, and record type, which is something like persons or group quarters facilities, or rather persons or household/group quarters facilities. For each of those combinations, we form a simple schema that just says this is the universe of all possible record types that we could observe within this data product. So a simple way to form this for PL94 is just to say PL94 needs to support queries that could be expressed over record types that look like a person is either voting age or not voting age. They are in one of 8 categories for HHTQ. Either they're in households or they're in one of the 7 major group quarters facility types. Hispanicity is whether you reported being Hispanic or non-Hispanic, and then race is kind of, I think, something I referred to before when Anand asked the question. This is the all possible subsets of the 6 major race categories, with one of them lopped off because there's an edit constraint that says you shouldn't be reporting, or we shouldn't be preserving that you recorded having no race, and so it sort of insists on imputing a race in there. And so you get 63 instead of 64 possibilities. Okay, so given this setup, which allows us within a particular data product and record type, we can then focus on an individual geographic unit, again, something like Texas in the set of states. And for that geographic unit, for this current data product, we can say, oh, okay, now we can express all possible record types we have. We're then going to generate a histogram that represents the microdata that we want to produce for this particular geographic unit. I'm not being terribly specific here about the particular measurements we're going to take for that geographic unit. In part, that's because there's an algorithm that determines that. We'll talk about it in a second. But a key point that I want to sort of highlight here is that these histogram objects can be, not surprisingly, quite expensive to store, especially with the way we're handling them right now, which is we are storing most of them explicitly in memory. And you can sort of wander along in increasing order the combinations of data products and record types we have. And you can see how quickly these grow. Now, if we had to store just a single sort of 85 million 64-bit floating point numbers NumPy ND array, that wouldn't be such a big deal. The problem is these numbers tend to get multiplied by the number of geographic units that are contained in an immediately in the geographic unit that contains them. So like all of the counties in Texas, for example. And sometimes that fan out can become very, very large and can multiply these numbers by 100 or 1,000 or something. And so you quickly end up, I think 1 million 64-bit floating point numbers is something like 0.07 gigs, which is not terribly expensive. But when you start multiplying it by 10 or 100 or 1,000, you quickly get into RAM figures that are a bit more concerning, or a lot more concerning when you start seeing RAM exceptions thrown. So why are we insisting on using these histogram objects given that they're very expensive and in general you don't necessarily need to rely on them? There are a few reasons. They're not really all listed here, but the quick ones that I have are it's easy to guarantee that the limit as epsilon runs to infinity of the DAS, it will be the true input data. And this, while it may not be a terribly important feature in sort of general applications and when you have sort of a quick list of the queries you're interested in, for interpretive purposes and working with sort of the folks who are going to actually set the privacy loss budget, which will not be us, but will be executives sort of several levels above my head, for working with those folks and explaining to them, hey, this is how our system works, it's really convenient to be able to say, well, if you were, maybe you won't, but if you were to just take your epsilon and make it as big as humanly possible before we run out of the ability to express that number in the relevant data type, you would get this F back. And so there is at least this sort of rough interpolation property in the limit. In addition to working with these histograms is, and this is probably the more important of the two reasons, I think we probably could get the limiting condition without worrying about storing these histograms all explicitly. Really the bigger reason that we need to work with them is given the complex set of invariants that we've had to deal with and that we've had to sort of try and make an algorithm that can produce feasible data under, that turns out, unless you want to code up your own sort of state-of-the-art convex optimizer, that turns out to be a lot easier if you can express variables that are sufficient for actually detailing all of the structure of these invariants. And the simplest way to do that is just to have access to the full histogram of possible record types, because that allows you to sort of express arbitrary invariants or linear expressions. Okay, continuing a little bit more on how the DAS sort of organizes its labor. As I said before, it walks down the central geopath. Within that central geopath, the reason we're moving top down, the motivation for it, is that this does a much better job than, for example, starting at the bottom and kind of independently handling each block and then sort of aggregating them together. It avoids the linear blow-up invariance that would contribute, and instead uses sort of borrows strength to try and improve the accuracy as we move down the tree by using patterns that are easier to detect higher up in the geographic hierarchy. And so that's why we're moving top down. In sort of a quick sketch, you can think sort of in pseudocode of the way the DAS works for a particular data product product, a record type combination, in really two phases and then sort of a looping phase. The first phase is it's going to take all of the measurements for all of the geographic units over the entire hierarchy that you're interested in. It will do this using something known as the high dimensional matrix mechanism, which this talk is not about, but I believe there's at least a conference paper that you can Google and pick up pretty quickly. Some of our academic partners put together this algorithm. It is a refinement of the matrix mechanism that is intended specifically to approximate the kinds of strategies and the structure we see in sort of the tabulation sets we're interested in publishing, and to use the structure that we can find in those tabulations to scale up the matrix mechanism to much larger sizes than is really feasible with sort of the actual matrix mechanism or sort of common variants of it. Given that you have these measurements, we now move into sort of phase 2.1. Phase 2.1 is, well, we don't have any microdata yet, so starting at the national level, let us build an optimization model that will allow us to sort of perform inference, and that inference will consist of generating a microdata's detail file for the nation that is consistent with the invariants we have at the national level, and that is also fitted to sort of the observed estimates of these workload queries, given the measurements that we took. There is a little bit being hidden here in the asterisks. It turns out it's actually not sufficient to fit just to the invariants at the national level. There is information you have to percolate up from the block level, or you start running into all kinds of infeasible optimization problems all over the place, and that was a headache for quite a long time. But we don't have time to talk about that today, so I won't say any more about that unless folks want to talk about it after. Finally, we just sort of repeat this process. So now for every geo unit where you currently have an MDF and you don't have an MDF for its children, go ahead and generate the MDS for its children by solving a large-scale simultaneous optimization problem that does inference over all of those children for that geo unit. This is just another visualization of what we've already said. I don't think I'll linger on this very much, but make MDF at the nation, then simultaneously for all of the states, given that you know what the nation looks like, then for each state, for all the counties in that state, given that you know what the state looks like, et cetera, et cetera. Okay, so as I think I've sort of hurriedly said a few times, this is a very, maybe I haven't, this is a very abbreviated description of how the DAS works. A longer talk specifically about the DAS would focus more on it. I now want to transition to sort of what I was asked to talk about, which is sort of practical obstacles that we've encountered in working with and developing the DAS. And so I'll just say there's still a lot left that has to be done and decided, but we have gotten a lot done, and we've also run into some interesting obstacles along the way. So I will talk about two classes of obstacles, the same two I mentioned before, so I won't repeat them. And these are those two classes of issues. Just to remind you, the first is sort of error estimation and how we're going to present error estimates to our end user community. And the second is implementation issues, which is sort of my catch-all term for not being able to come up with a more creative and precise name for what implementation issues consist of. Okay, so error estimation. Error estimation is something that frankly, we haven't had a ton of time to work on to date, but having considered our options, we can see there are going to be some fairly significant problems in trying to figure out how best to do it. But we're really, at least I'm really excited about it, because I think it should be one of the sort of key sales points for using a formally private approach amongst sort of general user communities. We couldn't do this with prior methods. We couldn't publish our code that we used to do DA. We couldn't, and I think I'm preaching to the audience probably largely here, but we couldn't publish our code. We couldn't tell people the parameter settings we were using, and we certainly couldn't provide sort of precise, well-described estimates of the error or the structure of the error that we were infusing. We want to be able to do that because that's not the point, but it is a nice side benefit of adopting formally private methods. Unfortunately, doing this poses some hard questions, and I think these last two things are a little bit redundant, so I'll talk about them in a second. So why is it hard to do this in practice? Well, I mean, the most obvious thing we could do is just say we have this gigantic workload that consists of like 150 billion tabulations that we might possibly try to publish. If we do that, are we just going to go to every single one of them and try and publish an error estimate associated with it? And for some methods, actually, that could be okay. So if the method you're using has like a nice closed form for the error associated with it that is independent of the underlying data, and there are lots of examples of this in the DP literature, then you're kind of in a good place, and you could just say, okay, I'm just literally, it's cheap usually to compute these, I'll just go to every query and publish an estimate of the error. And you're sort of done is maybe a strong word, but you've accomplished the primary task at that point. A good example of this is the DAS's reliance on HDMM. Sort of at the core of it, HDMM is sort of, again, a refinement of the matrix mechanism. And in the last step, what you're doing is just taking linear combinations of noisy measurements that pop out of the Laplace mechanism or the geometric mechanism, or whatever other primitive mechanism you want to sort of insert at that final step. So if that were all we were doing, we would actually, I think, be in a pretty good place as far as generating the sets of error estimates that we're interested in. Unfortunately, error estimates of that kind within the algorithm we've designed would miss a whole lot of what we're doing and not reflect sort of end-to-end what the error is actually going to look like after the complex post-processing and also the sort of complex incorporation of invariants that we're doing. So in particular, they wouldn't reflect non-negativity, So non-negativity, performing that non-negative inference, as far as I know, there is no nice sort of closed form for what that error is going to look like. For incorporating invariants at the same time, which are sort of fundamentally data dependent. For incorporating integrality, which is always a headache. Whenever integers are a part of your requirement, things can become difficult. For proceeding top-down, this is actually something I think we could remove. So if we, in isolation, focused on the top-down issue, we could actually sort of probably adjust HDMM's error estimates and sort of its RMSE expressions to reflect the fact that we're doing this top-down work. But we can't do it at the same time that we do these things in the first category. And finally, so from conversations internally with a lot of the folks who are responsible for data review and who have more expertise being closer to the data than us, it is sort of apparent that while absolute error, which is what HDMM sort of focuses on optimizing, is important, a lot of our internal reviewers and experts' intuition is also sort of about relative error as well. And this sort of varies depending on the size of the underlying query. Not just the relative error, but also whether they care about relative error or absolute error. But in order to incorporate this, we need something that can look at the data, and that's not what a data-independent closed form is going to give us.
So I guess at the risk of confusing some of the users, you could just publish the results of the HDMM part, which will give you numbers which are not necessarily consistent, but at least unbiased and have good error estimates. Have you considered doing something like that?
So when you say publish the numbers that are the result of the HDMM part, do you mean just the raw estimates themselves, not the final microdata? Yeah. So we have, or at least I have, and I've tried to push people to maybe consider that. I don't know where we sit as far as that decision is concerned right now, but my inclination is to sort of push for the more categories of information we can provide with important caveats and flags about which sort of group of users we're expecting to find them useful and not confusing, I would like to lean more towards releasing that information than not releasing that information. But ultimately not my decision, so considered but not decided. Okay, so there are actually several other approaches, but the other one I'm going to talk about today is there's at least one other obvious approach for addressing some of the shortcomings of just having those closed form expressions that miss a lot of the categories of information that are involved. And that's we could spend a privacy loss budget, epsilon, explicitly estimating the L1 or L2 or whatever class of error it is you're interested in. We could spend it explicitly estimating the error on a bunch of our queries. And if we do that, that helps in some sense. It does give us, for whatever queries we target, it gives us, immediate end-to-end estimates of error with, I think there are fewer structural assumptions people expect of us for these final error estimates, so we wouldn't have to do any crazy complex post-processing of them, and so we could just stop and say, hey, here's this simple distributional description of the error that is in this error estimate, and I think that would actually be quite nice. But of course this comes with problems too. Most obviously it costs privacy loss budget, and we are already running a little thin on that given that we have 150 billion queries that have been floated as sort of a conversation piece. And that sort of poses the same question as indicating or specifying the workload in the first place, which is, okay, we have this massive complex workload, W, how do we now go about choosing which queues to spend privacy loss budget on to estimate errors, given that we already know it's sort of a gargantuan task to decide how to do that just for specifying the workload in the first place. And that's sort of an obvious problem, I feel like. There are also some slightly more subtle, not super subtle, but slightly more subtle problems that also occur, or at least questions that are raised. So if we do spend this privacy loss budget, so say we take our original noisy measurements on the things that we want to get low error on and treat in a differentially private manner, we then do our complex post-processing to get the final microdata that we want to actually produce at the end of the process, and then we spend extra privacy loss budget estimating error on a bunch of the queries that we just produced, or that are of interest over that microdata. Those queries now, of course, have information. They carry information about the true underlying data, right? So we are then tempted to say, well, we don't want to throw privacy loss budget away. Let's now use those to improve the microdata that we use them as an estimate of the error on relative to the true data. But if we do that, then the estimates are no longer good estimates of how well the microdata is doing, and so we kind of enter this feedback loop, right? And it's also a really expensive feedback loop because you're spending privacy loss budget every time you step forward in it. And so it's not totally clear to me what like a nice satisfying resolution is to that question. There's also at least one other category of concern I had here, which is that supposing we do both of these things in some measure, they have sort of different characteristics. Some have advantages and disadvantages in different areas. How do we maybe combine them in some way that could be useful? Or do we just publish both of them and say, hey, here are sort of in our experiments and analyses, here's where we think this performs well and where this doesn't perform well. And so there are some interesting questions surrounding how should this multiplicity of error estimation methodologies that we have available to us be marshaled together in a way that will be coherent for external audiences and will compensate for the disadvantages of the different approaches. And hopefully not magnify the disadvantages. Okay, so that sort of does it for error estimation, and I think we're actually doing okay on time, which shocks me a little bit. So that covers the error estimation sort of practical problems topic. Now I'm going to jump into the implementation issues topic, which again, terrible name, but hopefully it'll be clear what I mean. So I'm going to sort of articulate two major categories of practical issues that I group under this topic. One are policy issues, which I really can't say it better, I think, than I wrote it down here. They emerge exactly because in a large statistical organization, there's a huge number of people involved in generating, if it's a large product anyway, in generating any individual large product. And so there's certainly a large number of people involved in generating the decennial census. Given that, and also that they're not all going to sit down and study and care about and become passionate about differential privacy, it can be very difficult to sort of figure out what sorts of rules need to be articulated and imposed to make sure that we don't accidentally release or encode in our other releases some sort of non-formally private information about the data product. And so this is one class of concerns. A second class, which I think has actually been looked at in various ways in the literature before, is that there are often mismatches between the sort of mathematical idealizations, the information theoretic idealizations that we tend to work with in practice when describing our DP mechanisms, and the actual implementations that we use. And so I'll talk a little bit about that as well and some low-level issues we encountered. And I don't think, answer how to fix all of those problems, but hopefully just call more attention to them. Okay, so this is just a quick run through of I think what I largely already said, which is that in a large stats organization generating something like the decennial census, there's a lot of people involved. And also a common instinct for someone who is accustomed to doing data quality review and who knows that you're sort of building this really fancy new algorithm that is based on an entirely new methodology, a common instinct is to say, well, I want to make sure you didn't screw up. And for example, I think as I was asked earlier in the talk, I want to make sure you didn't introduce really large errors that should be signals that there's something going wrong. And so a natural instinct is, well, I want to look at the true data, the Ceph, and I want to compare it directly, subjectively, manually to the MDF, the final privatized data. And then I want to compare the two and say, whoa, like that block looks really crazy, that doesn't seem okay. And then I want to kind of talk about that and escalate that and discuss it and sort of see how can we fix this. The only problem is this is sort of blatantly non-differentially private, right? You can't have this subjective human feedback loop built in that says, well, you know, while the DP thing is kind of cool, we don't really want to respect the random dice rolls. We sort of want to insert sort of our own judgment about whether or not that dice roll was okay. And so this poses kind of a hard problem, really with two facets to it. One is the obvious one. How can review processes sort of reasonably be structured so that we avoid this problem, but still get reasonably high quality review? And second, if the sort of restrictions in this category involve just saying, look, the way in which people can make these kinds of comparisons is severely restricted and what can be done with those comparisons is even more restricted. If that's the case, then how do you go about convincing people, especially people who aren't going to be interested in digging through the details of your code and going and evaluating it on a bunch of external data sets, how do you convince a group of folks like that you have generated a high quality product and that it's sort of free of bugs? And so this is kind of a hard question, right? Because not everybody is working on these algorithms from the algorithms end of it. A lot of people are working on it from sort of the, we're interested in the quality of the end data side of it. And so we need to have a way to reach to these communities and say, well, look, here is a reasonable mechanism, a reasonable way for you to evaluate this data that sort of feels reasonable to you and sort of helps you build intuition about why it is or isn't working the way it's supposed to. This is another sort of, apocryphal is the wrong word, but made up story. So this is a fictitious story that keeps me up at night because I have weird dreams, I guess. So suppose in its production run that the DAS is running and it throws an exception. Specifically Spark throws an out of memory exception. I haven't described what Spark is yet, which is a mistake, but it's sort of the large scale parallelism system that we use to organize most of our computation across a cluster. So one of the things it likes to do is say, hey, you're throwing way too many memory requirements at me, I'm just going to shut down and not finish this job. And so if that happens in the production run, I can imagine a future, hopefully one that won't happen, and that we can sort of organize our policies to avoid, but I can imagine a future where a friendly engineer might have SSH into one of the nodes because he's like, oh, this is really exciting, and like this is this cool new thing that's running, and maybe the engineer notices that the nodes are running close to their full RAM usage, and that they're about to run out of memory. And so given this termination, the engineer then says, well, hey, maybe for the next run we should increase the size of the machines that you're running these on. So they do that, but unbeknownst to us, although hopefully we would figure it out given that it's like my example in this slide, the DAS may have thrown that error because sparsity was lower than we were expecting. I don't expect that there would be large variations in sparsity, but there could be enough of a jump that suddenly the sparse data structures we use all over the place are not as efficient as we thought they were, and we run out of RAM in the production run. And so that's great so far. Maybe then we get a bit excited and we say, hey, there's this cool newfangled thing that we designed that's intended to protect privacy. Here's how we did it. And specifically, we're going to go so far as to, in the name of the kinds of transparency that differential privacy allows us to share with you, we're then going to release our machine specs too and say, here are the CPUs, here's the RAM, here's all of the specs for the machines we used. But unfortunately, we now have this problem where, well, the query RAM of top of Ceph was non-differentially private. And I'm not sure that you can expose a practical vulnerability based on this, but I also would rather not gamble on that. And sort of I interpret most of our move in this direction as an attempt to minimize these kinds of things. So this sort of keeps me a little bit up at night because it seems very hard to nail this down, especially when you're in an organization that is large and dispersed and where you as an individual don't have sort of direct control and access over all of these systems. And again, not everybody is sitting down studying differential privacy at night necessarily. Okay, so that's the first, I think it's the last of the policy issues actually. I think I said that we were moving into technical and I didn't. It's sort of quasi-technical. So let's move into the first of the actual sort of technical facing implementation issues. So I just want to mention, I think probably a lot of folks in the audience are familiar. If you're not, I recommend checking the paper out. It has been shown before, so maybe two things to say. Generally speaking, naive implementations of DP mechanisms can fail to actually be DP in practice when you start taking into account things that you hadn't modeled previously. I don't think there's anything super surprising about that. What is more interesting is that Ilya Mironov showed, I think it was a solo paper, could be misremembering, but I believe Ilya showed that the difference between floating point numbers and the reals that we usually use them to approximate can actually be really important for differentially private mechanisms and can totally undermine your guarantee, sometimes in highly practically important ways. And so this was interesting to us because, well, as sort of newcomers about 2.5 years ago to DP, this kind of thing was completely not obvious to us. And so learning this, I became a bit more aware, I think, of trying to watch for low-level assumptions that we were making without realizing it. And so we started to wander across a few. None of these are, I think, necessarily entirely novel issues, but they highlight the kinds of problems that can sneak into a DP implementation at scale, especially if you're sort of struggling to meet problems of scale, and so learning systems that you weren't a complete expert in when you moved into the environment originally. So one of these involves NumPy's Mersenne twister. So most of the DAS is implemented in Python, and NumPy is a key library that we use. And the second is about Spark and the accidental sort of correlation between streams of random numbers. So this first one, Mersenne twister. The Mersenne twister issue is interesting. It's been well known for a long time, as far as I can tell, that Mersenne twister is not cryptographically secure in any reasonable sense, and that you really shouldn't be using it for sort of security applications. That being said, this was not an area that I was an expert in, and so I was interested to learn that, oh wow, Mersenne twister is not something I should be relying on. And to learn furthermore that it's the only pseudo-random number generator that is, by default, available in NumPy. And there appears to be, at least in the current commit of NumPy, no way to override it. We have some workarounds at this point that are more and less hacky depending on which one we're talking about, but this was a bit of a shock to me. Especially since on thinking about it in a bit more detail, I think this actually exposes sort of a reasonably practical vulnerability, not just sort of a theoretical failure. In particular, so the way, this has gotten kind of blurry, but the way this function, which is sort of copy and pasted from the commit listed up there, works is this is an implementation of Mersenne twister. It spits out at the end 32-bit integers, and those 32-bit integers are generated primarily by looking into a state of random numbers that are currently in stock, of 624 of those, and sort of taking one out and doing the sort of tempering operations down here to them. And every time you go through 624 consecutive random draws from Mersenne twister, it then uses this sort of complex looking stuff up here to say, oh, we've reached the end of the length that you're allowed to use. We now need to reset sort of our queue of available random pseudo-random numbers. And that's what this stuff up here is doing. But the key point is, in between every 624 iterates that you draw from Mersenne twister, it's not calling this sort of complex looking code. It's just kind of grabbing whatever the next value is and feeding it to this tempering operation. And this stuff down here is completely invertible and really cheaply invertible. And it's not even terribly hard to write down some code that will invert that. So you can, if you have direct access to draws from Mersenne twister for like 10,000 iterations, you can just go through and say, okay, give me all those draws, I'll invert each of them, and then I will just sort of walk back in consecutive blocks until I figure out which one of those plugged into this part and into the full body of Mersenne twister reproduces all of the other observations I got from Mersenne twister. And when you get that, then you know you have perfectly reproduced, or at least with high confidence, you know you've reproduced the Mersenne twister state, which means you can now predict all future draws from Mersenne twister, which is a problem if you're relying on Mersenne twister for something like the DAS. And so, maybe I should have switched slides a bit earlier. This is sort of most of what I just said. The only thing on this slide that I think I really want to highlight is this stuff at the bottom. So, there are a few requirements to carry out that attack, that Mersenne twister-based attack. The most obvious one is you need at least a modest number of draws from the Mersenne twister sort of subroutine. And it may not be obvious that you can get that many random numbers. But in the DAS, if you remember the billions upon billions of tabulations that we're considering publishing, That's a lot of random numbers to look at. Even within each geographic unit, we are publishing sort of at least 2,000 estimates for the PL94 case. And if that is its own unique stream of Mersenne-Twister iterates, you have more than enough to sort of try to carry out that attack. If you jump up to SF1 persons or households, this number is 500,000 or a million, and you definitely have enough. There is some stuff here that I'm hand-waving. Maybe we should get to this part first. So even when you've seen those are iterates typically, and let's forget about the post-processing for a second, which is another thing I'm going to hand-wave away. But pretend that they are just like literal geometric mechanism or Laplace mechanism. Laplace is easier. Laplace mechanism outputs. So they all look like the true value x plus some perturbation. There is still sort of extra inversion you need to do because the implementation in NumPy of the Laplace distribution actually uses, I think, 2 32-bit integers, not just one, and not all of the operations are sort of one-to-one invertible. You have to do a little bit of like set-valued inversion, and then you need that mostly means that you need more than sort of the lower bound number of numbers to carry out this attack. But I don't think there's any reason you couldn't scale that attack up, and especially if you had 500,000 or a million possible outputs, I don't think there's any reason you couldn't figure out how to do that inversion. And most importantly, it may also be the case that when you look at each of those individual values, x plus perturbation, you say, well, okay, but there's also the true value in there. There's also the true value in that x plus perturbation. So how do I get to the true value? I don't want the true value, I just want the perturbation in order to carry out this attack. How do I get to the perturbation? Well, when you're generating this many values and most of them are 0, it's not implausible that an attacker could look at an individual geographic unit and say, well, I know there's only white people in that block. I know everybody's Caucasian there. Because I know that, most of the counts that are published must have a true value of 0, and that immediately tells me what the perturbations look like exactly for the remaining tabulations. And that's exactly sort of the fertile ground you need to carry out this attack. And so this is, I think, quite concerning and a very good thing to try to avoid doing or allowing. So given that I have 5 minutes left, I'm going to go a little quickly through this next example. The point of this example is that if you're not familiar with Spark, Spark is a really nice system for coordinating sort of cluster-wide parallelism. Spark sort of looks like this. This is like the toyest of toy examples. You have a thing called a Spark, I forget what the first one actually is right now, but it has a Spark context underlying it. You call this parallelize operation to say I want to take this sort of Python list and I want to break it up into units that can be distributed in tasks across the various cores available on my machines in my cluster. In this case, we're telling it split this thing up into 2 parts. It's not a guarantee, but usually those 2 parts are going to be the first 2 elements and then the last 2 elements. If that is the case, you can then really quickly implement the Laplace mechanism, and I sort of haven't put any of the constants in here, but you can pretend I did. But you can implement the Laplace mechanism and say, okay, well in here we're going to map over each of the elements that was in our list and add Laplace noise to it. And sort of naively, this looks like, oh hey, I implemented like my very first Laplace mechanism, great, in Spark. Unfortunately, if you're not careful and you just do it literally in this fashion on a Spark standalone implementation on a single machine, we haven't been able to reproduce it on a cluster just yet. This yields a vector, so they were all zeros originally, remember, a vector in this case just of the perturbations with the property that x1 and x3 and x2 and x4 are perfectly correlated. And so this is a problem. Now our epsilon zooms off to infinity when we were kind of hoping to hold it down to a finite value. And that's trouble. We don't want that to happen. So this is sort of another example of how a really useful system for enabling large-scale efficient computation at the scale that we need for a real-world application nevertheless sneaks in a whole bunch of low-level problems that are kind of hard to ferret out and make sure they don't occur. And this is, I think really the problems are really more my interest here. But if you have ideas about how to solve the problems, that's what this slide is about. And then we'll drop to sort of my closing thoughts. So I have this really long list, which I'm gonna drop one slide down and then jump back up. I don't really want to go through them in detail because these are mostly things that I wanted to talk about today, but didn't have time to talk about. We have a longer list of things that are concerns and are sort of practical barriers to implementation for these large-scale projects, especially in the presence of complex post-processing. And then this is a sort of a closing slide that says we've done a lot of work and we've gotten pretty far. I think we're on track to get where we want to be. Currently, the DAS code is sufficient for handling the PL94 data product, possibly with the inclusion of a citizenship voting age table, which is not my decision, but could very well be there. And then we're continuing scaling tests for summary file 1. That's sort of where we are currently at in trying to take our code and say, hey, okay, it works for PL94 with or without citizenship voting age tables, but can we now move it to SF1 with the current code base? And once we get to the point where it actually functions on SF1, then we would like to say, okay, we know it's actually not going going to work for SF2 or ANSF, so now let's develop sort of an entirely different approach for those. And we have shared a few ideas about how to do that, but that is far from a settled topic, and there's a lot of conversation that needs to happen around that. But I think it's going to be sort of fun and painful, but also fun working through the rest of those problems. And so I will close by just sitting on this slide. Thank you.
Time for some questions.
So you've mentioned a couple of times that you had various headaches. Consistency headaches, the fact that you're working down and having to be consistent on levels and so on. So I could see two kinds of problems. One is computational and the other is loss of privacy budget. Can you point to the places where, because of, in some sense, arbitrary restrictions, you're spending much more of your privacy budget than you would like? In other words, if you didn't have to be consistent and you didn't have to have I and so on, how much would that liberate you, and in which parts of your work would it liberate you most?
So I think the biggest impact that dropping invariance, and I also throw in sort of the microdata requirement that we produce microdata, dropping those two requirements would mostly, I don't know that I have representation of it here, it would mostly have taken a period of a year to a year and a half of work that was entirely focused not on optimizing sort of the accuracy privacy trade-off, but was instead focused on saying, as we walk down this tree, we need to know that there's not going to come a point at which the algorithm just says, well, I can't make microdata that is consistent with all the requirements you've given me. It would mostly take that period of time and allow us to instead convert it into trying to improve the privacy accuracy trade-off, which I don't think quite speaks to loss of privacy loss budget or gain in privacy loss budget from dropping those requirements, but I think does speak to sort of the amount of time that is diverted from sort of the primary activity. It's also difficult because things like the invariants in particular there isn't really a clean translation, as far as I'm aware, of them into sort of this is the amount of privacy loss budget we've lost because we imposed these invariants.
Sometimes, like, you sort of double the privacy loss because you can't have in versus out. You have to keep the total number fixed. So.
Right, and you can sort of adapt those arguments to things like blowfish privacy and some of the other frameworks that have sort of privacy loss measures still associated with them. I think what we've seen is mostly if we were to take that route to quantifying the effects on our semantic guarantees of these additional sort of restrictions that we have, that the guarantees would be very, very bad. The epsilons in practice for almost any sort of standard value would be massive when we actually look at sort of how the posterior odds ratios that we're trying to bound behave. We have alternatives to those that we've tried to work out semantics for that are more nicely behaved, but instead of trying to sort of bound the worst case under an altered definition that respects the various restrictions imposed, we instead try to say things like, well, there are certain attackers, classes of attackers, and there are also certain hypotheses that we just can't guard against. And so that is a somewhat more fraught exercise and a little bit further from sort of the ideal of guarding against all possible attackers that we kind of like to be close to. But giving those things up has enabled us to sort of drag the bound on posterior odds ratios and those sorts of objects a little bit back down to earth. And I can share some of that after if you're interested in. I think we have some of that in a point where, well, I'll have to look at it a bit. But
We have more questions probably.
First of all, thank you for this overview. I feel like you gave 5 talks in the speed.
Yeah.
So there's a lot that you might have said that I missed, but I'm going to ask 2 questions and you'll tell me. The first one is, at the very end, you said we need new measurements and forms of data collection, or something to that effect in one of your last slides, and I'm curious what you mean with that.
stop me when you see the slides you were thinking of.
It was at the very end, I think on the
At the very, very end?
Yeah.
So here?
One more.
Let's try
In your final thoughts, I think that, anyway, but so you made the point here. Different measurement and microdata generation methods in your first point there. I was wondering.
Oh, for SF2 and ANSF. Yeah.
And then my second question is related to this issue that you mentioned, sort of 2/3 along the way. The having knowledge about a particular census block and the absence of people, you said that can be solved, but I was wondering sort of how you're going about that. Who makes the decision on, you know, how much knowledge you can have? I mean, you made this example. If you know there are no black people in the block and you put someone in, so I mean that I didn't really fully understand what you have in place systematically to overcome it.
So I'll take the first question first and then jump to the second question. So for the first question, I will say first this passage about needing fundamentally sort of different measurement and microdata generation methods is very specific to SF2 and AINSF. And really what's driving this is just that throughout the rest of the algorithm we have these massive histogram objects wandering around, and they're usually reasonably compact because they're very sparse, but the ones that contain measurements are a whole lot less sparse. And so when we move to SF2 and AINSF, we know that those histogram objects are going to be 1,000 times larger, and there's just no way to store them. So instead we need some sort of iterative algorithm that will just store exactly what we need when we need it, and we'll sort of throw away and reclaim memory as needed. And I think we can achieve that for SF2 and AINSF, and my guess for why that's possible is that the primary thing driving our need for those complex large histograms was that the complex large histograms, they enable us to handle the complex invariants. But for SF2 and AINSF, once you've conditioned on having sort of dealt with SF1, the remaining sort of stuff that has to be done doesn't really involve complex invariants. And then for your second question, which I think was about who decides or systematically how do you figure out how much knowledge is allowable, I think the reality is that there is not a good answer for that question, which is why we have tried to only partake in any sort of exercises of that kind when it is absolutely required. Which is, so when we're dealing with the invariants, it doesn't seem to be avoidable. If we're asked to choose between, or to provide guidance to others to choose between invariants at the block level versus the state versus the nation level or some such, then we need to try and reason about those kinds of things. But for the final guarantees, we're trying to do our best not to make decisions sort of personally on how much knowledge is reasonable to allow. Because I think that is a very difficult thing, and that's sort of why it's attractive to move towards these very broad guarantees. I'm going to try not to harm them too much.
Okay, so let's thank again.